Hi folks, this time we are going to talk about two other quantities that are measured in electricity. We are going to talk about resistance, and then later we're going to talk about power. But let's begin with resistance. Resistance in electricity measures anything that resists the flow of electrical current through a material. I like to think about it as electrical friction. What gets in the way of those charges passing through a conductor? So we talked in the last video about the fact that when you have current going through a conductor or a wire, you have a charge going in one end, and it's not this like that charged particle itself comes out the other end, but this bangs into that one, which hits that one, which hits that one, and boom, 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 boom. That push goes all the way to the other end, and the energy gets spit out the other end of that conductor. Well, in some materials, like insulators, that doesn't work very well. This is a model or a sketch of table salts. Table salt is an insulator. It's non-metallic, and all of the atoms are stuck. They are bonded in very strict locales. All of the electrons are bonded and they are not free to move. There is a tremendously high electrical resistance. There is not a clear path for the electricity to flow. So it's very difficult for electricity to flow through something like an insulator. Something like a conductor has a very, very low electrical resistance because in a metal, surrounding the individual nuclei of the metal atoms, the electrons are free, and they are free to kind of wander around in sort of a fog around those metals. And so when the electron comes in this end, it bops into another one who bops into that one who bops into that one, and they're all free to move very, very quickly from place to place, and there's a very low resistance to electricity. Now, electrical resistance produces heat. When you have this path of electricity going through a conductor, as it is trying to hit one charge hitting another, hitting another, hitting another, as it's moving along, every one of these bumps that along the way, it is going to have a collision, and collisions produce heat. There is some energy loss, and that energy loss very often produces what we can use in toasters and in stoves and in dryers. If there is a high quantity of heat produced, heat, as we've talked about in the past, is kinetic energy, and kinetic energy is velocity. When you get an awful lot of heat loss, these particles are moving back and forth really crazy. They are bouncing and there's a lot of motion involved. As these electrons are zinging through this conductor, there is so much violence to these collisions, there is a lot of energy lost. And energy that is lost as heat means that you have an appliance that is going to be hot. It also means it's going to be expensive. Some of the most expensive appliances that you and I use that are powered by electricity are ones that produce heat. Now, something like a toaster, if you use your toaster more than 15 minutes per day, you make a lot of toast, but you might use your stove a lot. You might cook a lot. You might have a large family, and you might use your dryer a lot. So it's a combination of how hot, how much resistance, and time that is going to go into cost. Electrical resistance is measured using a unit called an ohm. The symbol for an ohm is Greek letter omega. It's drawn like that. And it is named for a scientist. His first name was Georg. Sorry, I said that wrong. Georg Ohm. And it's a fun word to say. It's a fun symbol to draw. In electrical circuits, a resistor is drawn like a little sawtooth, like that. In circuits, a resistor like this can be put in the circuit. Why do they do that? To change the current, to change the voltage in the circuit to meet the parameters necessary for whatever's going on. This is a resistor that has a specific quantity of resistance or ohmage. The stripes, there are codes to help you understand what those stripes mean. And this is a variable resistor. Some people call it a pot. And if it looks like the volume control knob or on something, that's a common use for these variable resistors. They change the volume, change how high or low something can be set. So variable resistors are in a lot of different circuits. Now, the ohm is a fun unit. So let's have a few minutes of fun with the ohm. What do you call an ohm on wheels? Well, that's a mobile ohm, a mobile ohm. Oh, what do you call an ohm that is separated from a bunch of other ohms? That is an ohm away from ohm, ohm away from ohm. Yeah, I didn't tell you they're good jokes. Okay, what do you call 2 ohms sitting on a stove? 2 ohms sitting on a stove? Ohm, ohm on the range. Yeah. Okay, what do you call an ohm that is stretching way out? This is an ohm that is on the ohm stretch. He's on the ohm stretch. This is a dinner plate. When an ohm is on the dinner plate, he's on the ohms plate. Think baseball. He's standing on ohm plate. And this is a bunch of pictures of candy. And what's candy? Candy is sweet. So this is ohm, sweet, ohm. Aw, you need that sign up in your house. Ohm, sweet, ohm. This ohm costs nothing. So what is he? He's ohm free. He's ohm free. Ohm free. And this is the less than sign. Less than. So this poor ohm, poor ohm, he's ohmless. You got to give this guy a home. He's ohmless. And that's the end of the ohm jokes. They're bad. But they're fun. All right, power. We talked about power when we were doing work, energy, and power. Power is defined as the rate or the speed at which work is done, or electricity or energy, whether it's electrical energy or other kinds of energy, is used. This is a metric unit you're very familiar with. You've been buying light bulbs in watts for years. So power is how fast. We're talking about how fast energy is transformed per unit time into something else. 1 watt of power is 1 joule of energy per second. None of this is different. We've talked about this when we were talking about power, but just a reminder, this also applies to electricity. Now, when we talk about wattage of an appliance, we're talking about how fast the job can get done. So let's say you grab a Hot Pocket or some frozen meal and you want to cook it quickly in a microwave. So here are 1, 2, 3, 4 microwave ovens. Each one has a wattage, 900 watts, 1200 watts, 700 watts, 1000 watts. If you want to take a frozen meal, put it in there, and you want it to get it to the same level of doneness or hotness, which one's going to cook the food faster? Which one? Yeah, the 1200 watt microwave is going to do it faster. Okay. Which one is going to use the most amount of electricity to get this to the same level of doneness? Here's a kind of a trick question. They're all going to be the same because we're talking about to get this the same level of hotness, they're all going to need the same amount of energy that has to be input to this Hot Pocket in order to get it hot. But the 1200 watt microwave is going to do it faster than the 900 watt microwave. Wattage doesn't mean it's going to use more energy or be more expensive. It just tells you speed. Okay, let's try this again. Which one of these hair dryers is going to dry your hair the fastest? The 1875 watt, the 1900 watt, or the 2200 watts? Which one's faster? Yeah, the 2200 watt hair dryer is going to dry your hair faster. Will they all dry your hair? Absolutely. Will they all get them equally dry? Absolutely. All power is measuring is how fast. Use the same amount of energy, but it's energy per unit time. So we're talking about higher power, higher wattage, more unit quicker is what we're talking about. When we buy electricity, we buy it in things called kilowatt hours. Now a kilowatt, kilo is 1,000 watts, and a watt is a joule per second. And this gets a little weird and a little wacky. And then when you buy it from the power company, they sell it to you in kilowatt hours. So they multiply this crazy thing by hours. There's a couple conversion factors that need to go in here, but this is time. This is time. And if you throw some conversion factors in, the times will cross out. But I want you to understand what you're truly paying the power company for is energy. It is really an energy bill when you pay your electric bill. But they call it kilowatt hours because it's the combination of energy and time that goes into power. There is an activity that we typically do in class where we calculate the cost of running appliances. I just want to note that we can now do that, and you need this chart of data in order to do that. So I wanted that in your notes. Two other things before we leave this section, and we're going to use these pieces of information in our lab, and one is Ohm's Law. Ohm's Law is a mathematical relationship between current, voltage, and resistance, current in amps, voltage or electrical potential in volts, and resistance in ohms. This mathematical relationship is the cornerstone to circuit design and understanding really what's going on in circuits. So this is Ohm's Law. I wanted you to have that in your notes. And power in an electric circuit is determined by taking the voltage, that electrical potential, and the current, and that will give you power. And again, I wanted you to have that in your notes, and we'll spend more time in lab going through that. But that will do, and we'll talk next time. Bye-bye, my friends.